Okay, we have a question. 1 second. Let me send this email really quick. And then let's see what the question is. Person send that. Okay, get rid of that. Get rid of that. So we are making, let me make sure my sound is coming through. Yep, it is. Awesome. Okay, so we have a question on material from class 6, how to interpret radial probability and reading and interpreting graphs of orbitals, how to know many nodes, what type of nodes. Great. Awesome. So let's switch so we can see what we're looking at. Awesome. See if the student is here. Are you here? Mrs. Kane. And let's add this to the office hour. Time is about 30 minutes. Let's say 28 minutes. Talk about class 7 wave function graph and graphs that build on it. Radial nodes. Function graphs, nodes, and graphs that build on it. Radial. Okay. Ah, yes, I probably should share it. Good call. And anybody, and we'll make them editors. Done. Nice. Sorry. Okay, it's fixed. So let's kind of just treat it like an office. I typically don't just because a lot of this material, I don't want to go over necessarily things that are in the lecture, because apparently that, or not apparently, but that's not enough. We need to go further into what we are looking at. So let's see if I can even make my text like red or something. Let's see if it's looking to share it again, maybe. Okay. And I think we can. Yay! Hello! What is your thoughts on the wave function? I will place one below. So let's go to the Orbitron website. And I'm pulling from this. Oops. The wave function. What is it? I don't want that. I'm wondering what slides. Check Discord answered. Hi, I'm not the person who asked the original question. I'm not sure how to comment YouTube chat. You probably need an account, but I'm wondering what slides from 6-7 is not in midterms. And we should update something on our end very. So none of this is on the exam. So let's edit this and just clean it up. Bold. Able to, and we want to say, we should make it a little bit bigger, right? So let's put that in here. That's saved and done. Okay, so that person is done. Was it? I don't want that though. I think we have people here, so let's close this. Come on, go to see. Hey guys. I bet if I just something. It's 1:30, so let's try it. Ha, we got it. Awesome. Okay, back to this. Back to this. Back to this. And this is a student talking, I think. Another wave function. Okay, so we got that, and we need this one. The chat won't work as well, and I'm going to get back to this question here. Let's grab this. Okay, so that's done. Let's go back here. So, to my Emory person, before we go into what we're talking about, I want us to think about, or I want to hear from the student, the Emory student, when you look at these graphs, what do you know about these graphs? What have you reviewed my slides, reviewed my lecture, reviewed readings, looked elsewhere to understand them? What is your meaning for these things, Emory person? And while I'm waiting for that to come through, I will start covering this as well. So the different types of orbitals are sorted by those numbers, and the main ones we may want to think about first are N and L. N is the level of the... N is the... Well, let me ask them. What do you think N is? Well, we're waiting for the Emory person to chat. And again, I do go to Emory, but I'm not the original commenter. But I think N is. They are wave function graphs versus distance from the nucleus. But what does that mean? Okay, so we're getting close to that. Let's see what this student is saying. And is the energy level of the electron. Okay. So let me do my thing. So I'll come back in. Because we need I think a little bit deeper of an understanding. Sure, this is somewhat on the right track, but I want to know what is the difference between 1s and 2s and 3s and 4s, or 2p and 3p and 4p. What is the key to this number going up in terms of how we process the meaning of the number going up? Again, totally fine if they don't know the answer, but let's just kind of keep pushing carefully what we know. So, psi squared, yes! We're doing a lot of like back and forth here, so I should update my office hour timestamp to say that I'm talking about both of these things. I also ping pong a bit to talk about quantum numbers and L. So that's good. Okay, they're going to work on that. Which shows the probability of finding electron at a certain distance. Yes! Awesome! Great. So what is psi? Just nodes. In the Google Doc, how many nodes for A, B, C? And let's kind of say this one is A. We'll say this one is B. And we'll say this one is C. So I'm going to leave this kind of up here for a little bit. Maybe I can even put it closer. That'll be nice. Save some ring, some of this. Get rid of all this. The difference between S and P is the number of nodes. Ooh, this we need to be careful about. It's right, but I don't think it's the right way to think about it. It's right, but it's not. It doesn't. The shape, not number of nodes. And let me give a counterexample to prove them wrong. 2S and 2P both have one node. Is the orbital number? Yeah, great, great, great. Okay, so this is where they're confused. Let me show you some pictures of 1S, 2S, and see if you can see the physical, like, measurable difference. I will post here. Again, we're very, very, very happy to have them talking about this stuff. So let's see if I can find a 1S, 2S, like 3S quick picture. Haha! Perfect! Okay, let's copy this in. So what do we physically know is different? Yes, there's something with nodes. Absolutely. That is happening. That's one. But what is physically different about them? What are we seeing in them? Let's see what this person's saying. A has 0, B has 1, and C has 2. Yeah, great. Nice. This is what my class slide can help with. But let's take it farther. Let's take it a bit more in depth as to what and where the nodes are. So for B and C, what are the nodes? Radial or planar, which can include conical, but which, you know what, let's not. Conical is planar, but we can worry about that later. So we'll leave this here. But they're right. They're using a slide I have for class. Let's find it. Just so it's in the recording. And we have classes, and we have class day 6, this one. All right, and this can even, you know, go back and look at these. Boom. So there's this one and this one. Both of these slides are really important slides. Maybe I can highlight them just a touch. Well, you know what, we'll leave it. Okay, so they're working on that. Let's see what this person is saying. So let's make this a new question. Little sidebar. Slide 1 of the slide. No, you do not. I don't think you do. And let me even get rid of it for now, because this, you know, I'll leave this on here, but I'll put an edit in. Okay, let's move this over just a touch. Okay, that's done. No. Okay, so no. So let's go back to now this kind of answer. So first we need to really realize that this is, I think, a misconception. The difference between S and P is not necessarily the number of nodes. 2S has a node. 2P has a node. It's their shape. The letter SPD tells us what shapes we're looking at. Spheres, dumbbells, or Ds are, I don't know, 4 jelly beans sometimes. Great, we have another, I'm not sure. Okay, so I'm not sure how to determine this, and that's what I'm confused about. I'm also confused about how you know what subshell. Yes! This is what we need. So let me ask you some questions about this slide. Looking at this slide, there's something probably confusing to the Emory student. So here I have this note. Let's even make it white. So keep this in mind. I'm going to grab this idea and post it here. Let's make it 14. And it's like insert a horizontal line. So this is this question here. So this is the Emory chatter. And then this is the other person. Okay. So B and C have planar nodes, but yes, but what about the number? What do you see in terms of bumping the y equals 0 versus crossing? So you're doing great. This Emory person is doing awesome. They know a lot. They know how to count the nodes on every single one of them. They said no nodes, yes, because it never actually crosses y equal to 0. It never crosses the x line. Y never goes to 0 ever. Here y goes to 0 in the middle, but it crosses through. Here we touch y equals 0. We come back up and then we approach it again. And so we can make little notes about this. So student said, B crosses and C bumps. Yeah, great. So let's look at the P orbital picture of the surface area, not the side. What is the shape? And where is the plane? Versus the picture or shape of D orbitals, where is the plane? And so I got to post those a second, so let's kind of find some S and, or let's do P and D orbitals. Okay. I need more 3 dimensions. And I probably should put the nodes into start. Or it might be good for them to see that they're there. So let's just first do P nodes. Chemistry. Okay, great. So here is a bunch of P's. So this kind of builds, builds on B, builds on C. And these are me talking, so I'll do that, and then let's find some d orbitals. Great. So, I want you to notice that, again, this crossed it once. Does B have one node, so n equals 2? Yep, you're right. And C has 2 nodes, so n equals 3. Yes, also true. B crosses, yep, and C bumps. So I want you to notice that what planes appear at 0, 0? And do you see in the pictures above where those planes are and how they change the, like if we try to put another plane in the p orbital, we can't. The p orbitals are actually on the axis. And so if I kind of look a little closer at it, they are on the shape of the p orbital, we present it on the axis. So it's on the axis, but d orbitals, right, for the most part, these are 2. This is where the conical one is a little bit weird, but there are 2 conical nodes, so we'll ignore that one for now, even though it is still 2 coming out of the origin. Notice how over here, though, we don't have these little lobes actually in the axis. They're kind of put on the sides of the axis so we can fit more planes in them. Let's see how this student's doing. Careful, you are right, but what about the difference between a child, it's not a good idea, between what would be a good example? Kids. We're not quite noticing what I want to notice. The nodes are important and kind of part of the discussion, but we're still missing a fundamental concept of 1 to 2 to 3. And let's see what I said. At least I can bring it over and see if it helps at all. Haha, this is what I said. And I think I could present it better. So back to my Emory person as they're kind of thinking about that. Because I can tell the difference between I know this is P and I know this is D. I know that this is P and I know this is D because this one claims there's only one node in the as a plane. That's what I'm seeing here. There's only one node that I can fit in here. If I try to put another plane in here, any way I put a plane centered at the origin, if I try to put a plane in here, I can't fit another one. Whereas in C's orbitals, because apparently there has to be 2 planes at the origin. This one has 1 plane at the origin, this one has 2 planes at the origin. Only D orbitals have 2 planes at the origin when I look at their picture. Is that making sense to my Emory chatter on the YouTube stream? Let's go back to this person. And so let's get a couple of these things. So we've got like, sure. Ooh, careful, careful. It's so ugly, but I need to get a concept across to this student. Kids can go inside. Yeah. I'm liking this. What about you growing up from a baby to a kid to a student to an adult? Yeah, like they're getting close to it. I'm getting close to it. Okay, what do you mean it has two planes at the origin? So, what is the plane in this picture for my Emory person? What is the plane in this picture? And let's just look at one orbital before we look at all of them, even though it applies to all of them. Like, what is... And again, we'll kind of focus on what's an easy one to see. I think that one is pretty easy to see. So, I mean, for origin, I mean 0, 0, but in this picture, how do we describe this as a plane? Aha! Yes! Size. You are growing. So try again. Of not nodes, but what you noticed about you growing up. So let's kind of bring that down. This is great. It's a horizontal plane, yeah. It's I think of them as like a little piece of paper, and that piece of paper, as I extend it out in infinite directions, it will never touch the shape of the p orbital. However, if I slightly adjust this plane and try to put another plane in there, once I start angling this plane, because my orbital is on the axis, z-axis, because as that z-axis goes through that orbital, I'm growing across y and x, and I'm growing upward in z. So any other plane I put in here is impossible. There is no plane I can fit in here. There is no other piece of paper I can fit in here that won't touch electrons. But on the d orbital, how many sheets of paper are there? And notice where there is these z-axes, how they don't penetrate any of the shapes. The shapes have moved. It's a new orbital, and this is the size feeding into this. This says one plane at the node, so I can only fit in one. This says two pieces of paper, planes at the node, so I can fit in two. D's have two planar nodes. And so there's like kind of an addition I might as well add to this slide and say, and I'm sure there's a better way to explain this, and that's what we're kind of working towards here. Two horizontal and two vertical, yeah. And I'm not sure if this is clicking yet, but let's look at some pictures of some orbitrons a second. So 1s, you cannot fit a plane in here, and it technically extends infinitely outward, so there is no node here. This circle is only describing 90% of the space. Really it is, 90% of the probability of finding an electron. We really expand the sphere outward. When we go to 2s, we have a radial node in it, but still the origin has electron density. 3s, the origin still has electron density. 4s, the electron still has electron density. 5s, the electron still has density in the center. There is never going to be a 0, 0 node for any of these s's. And so when we look at their wave function, we should never have at the origin anything crossing or touching x equals 0. When we go to 2p, however, we can, let's look at the wave function. When we look at 2d, or 2, probably it's better to go this way. Let's go over here. When I look at 2p, I can fit a node in between it, planar, and when I go to 3p, I can fit another node right in between it, and now there's a radial node in it. When I go to 4p, there's now a radial node and another radial node in it, but still one plane. When I do 3d, I can see that there's 1, 2 planes. Go to 4d. There is 1, 2 planes, and now a radial node that's been added. And so there is a pattern here that we can memorize, which I recommend against, and rather visualize these orbitals, and they come out of an easier pattern, I guess, to recognize. S orbitals are spherical, p orbitals are dumbbells, d orbitals are little jelly beans that are kind of growing outward. Again, this is kind of the weirder one, but because I know the shape, that's where my quote-unquote memorization happened. I memorized the shapes of these things and saw where nodes were consistently, even as I went up in energy levels, which I'm talking about with the other student, even as they get bigger and get further out, even as their size increases. So let's see what we say here. Between orbitals and kids, it is about the growing of the kids. The orbital number n is telling us about nodes, sure, but what about size? And again, it's totally fine. So I'm just trying to kind of bring this idea back. In some ways, you know, again, I don't know if this clicks for you, but it's kind of like this principal quantum number 1, 2, 3, whether it is for the s orbital, for the p orbital, for the d orbital. You could think about it kind of like the age of the orbital. As it gets bigger, as the age goes up, as the number goes up, it's physically getting bigger. How big are your orbitals? And nodes as well. Yeah, great. And so yeah, the student just said, well, let's look at 4D. So if I look at 4D, I can see from its wave function, which is where the student started. Looking at the wave function, I start at the origin and I count 2 planar nodes, so it must be a d orbital. Then I go out and I say, oh, it crosses once, but this has to be a radial node. So I have 3 nodes, so it must be 4D. And because it has 2 planar nodes, that's why I'm saying it's D, and the other one is radial node. Yes. And so as I let's see, does it show a picture? No, it doesn't. So let's go back to this picture here. And maybe I can even just do a better one, 4D orbital picture. I don't love any of these. And that one's even different. Okay, let's go back to this person. Yes! Yes, we're getting there. Yes, yes, yes. Yes. And let me prove it. Yeah, why can't there be a 1p orbital then? Let them finish writing that. Great, so I feel like Emery is ready to move on to what is the difference between radial distribution probability and probability density? How would we know how to differentiate the graphs? So we're going to go back to this Emery person, kind of back out of this a little bit. Put that room. So for the next question, well, let's just go back to the 1s orbital. And we now have psi squared. Of that though. So this is psi squared. This is the question from the student. Answer with a question. And okay, if they don't know, we need to work through a lot of, like, this is a really difficult class. But I'm going to just make my own notes a second. Because this is kind of, I think, where we've gotten to. My other student has helped me realize this. The student that I'm working with on YouTube is starting to realize these things. Now we're trying to even go further past the wave function and what it means. How do you determine nodes? By taking the number in front of the letter and minus 1. Or so again, kind of just working back with the Emory student, what are the X and Y axes? And it's okay to say, I don't know. I'm happy to tell you, to remind you, to point back to the slides in class as well if you're not sure. Do you mean we cannot have a node for 1p? The idea of 1p means we can have no nodes as defined by the quantum number 1, but the shape of the orbital requires a node to be even made. So never a 1, only a 2p. And so let's kind of move this talk down. We're getting somewhere with it. Distribution of x's from distance. So this is really important, and I'll add it to this too. Psi squared y-axis is the probability of finding so it's a point. We're looking for it at a point. And I want to see if they follow that or not. It is even really strong students will struggle with this class. But this is where we're going to lose points on the exam, because we have to just say we need to know this to have the best model of the atom, which we need. Yes, in Chem 150, but it's going to be so pivotal for the rest of chemistry that we know what these things are and why we're making them. And I really should put all three axes here because these are three-dimensional objects. Wait for that Emory student to answer. The shape and size. Yes, okay, great. Wow. That's huge. this together. Okay. So I think you're doing great. Memory person still. We'll wait for them. We'll go back to this student. Jelly beans, 4 blobs. Yeah. 4 blobs. Yeah. Cool. Use previous icon to see other view. Previous and next icons. I think that this is the how does the stuff you're talking about with the other Emory student relate to all this? So this student is started asking me what are the quantum numbers, and I told them it has to do with the size and the shape. And they said, okay, great. I understand then that the electrons are being described by these different sizes and shapes, and so I want the student to see that what I'm talking about with the YouTube Emory student is, well, mathematically, how do we represent these? How did these shapes come to be? We didn't just make them up. They didn't just come out of nowhere. We didn't just decide for them to be this shape. The shape had to come from something. Yeah. see. I think I deleted the picture, but maybe I kept it somewhere. I did here, so let's bring that back down into our discussion again. Because again, it's kind of like I think part of what makes this tricky to teach is if the student's strength is math, we would talk about psi. If the student's strength was visualizing things, we'd talk about the shapes and then go to psi. Both are telling the same thing. Both are necessary for the exam, but you might feel more comfortable with one than the other. And so which direction to come from on this topic is more of a personal journey for students, and my quest is to try to figure out how do I explain both pathways at the same time, because it's a tricky subject. So let's answer this one here. This is a new question. This is a new answer. Okay, great. The shells or sphere surfaces are there's a good three-dimensional one. So that's what the student needs to see, is an eggshell. And that's a great way to explain it. Again, what I can't say enough of is that by talking to students like this, I get more clarity on different ways to explain it, and I'm starting to find out what I have not explained well enough. We'll be right back. Oh, no, 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 no. I'm sorry. I'm sorry. You can memorize almost like 70 things, right? About like what are all the answers to these nodes? What are size squares? What's the radial function? You can memorize like 80 things. But I'd rather have us memorize how to interact with these pictures and memorize how to interact with these graphs. Because if we memorize 4 or 5 more conceptually difficult things, the 80 things will fall out of them that we just generate by knowing how to deal with these things. Fixed. My in-laws are in town, so I was okay. This graph here has 3 nodes, right? Nope. So this is their question. I think that'd be. Maybe that helps. And let me Can I not do that? Oh, I probably can't. But I could do it on a paint. So let's do it on a paint. Okay, see, this is a breakthrough. This is exactly what we needed. Okay, okay, maybe. Okay, so we lost our discussion with the other student, but we've gotten somewhere with this student to about 1:46. No, that's fine. This sorry. Never be sorry. To learn. What is M? Yeah. M is the number of shapes, and the other M, don't worry about it. It just means you put 2 electrons in each orbital. And I should do it officially. What are the actual terminologies before I leave that? Blah, 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 blah. M sub L. M sub M of L. And the other one is M of M, M of S. Is the number of shapes. P has 3 shapes. D has 5 shapes. S has 1 shape. So this is their question. And this is my attempt at an answer. I think it would be a good idea to make some videos on some of these topics, because it is going to be where I think our class either performs better or worse than other classes, is how well this is understood. Because, well, I guess that's not 100% true, but certainly this would be probably where most students are going to struggle. What do you mean 3? Yeah, yeah. Yes. Let me answer this. Real quick check-in. Do you have chemistry background from high school at all? And remember how many electrons we put in orbitals, or how many p orbitals Okay. Totally fine. Totally fine. Totally fine. Cool. Cool. Okay. So let's get back to answering this then. To try. Because like this is kind of why you almost want to have electron configuration somewhere in this discussion, because it might activate prior knowledge, but also possibly not. Oops. Cool. So that's their answer. Oh, I forgot to take the picture, so let's grab the picture again. So this is kind of where we're heading. Yeah, what is the answer going to be? No, it could be. Like if they're not ready for it yet, fine. But it's kind of where we need to, or it is the not great connection I made in class, but well, maybe I made the connection, but it is so much that they got blasted with on that class day that assuming, you know, they just can't, you can't take it all in, I don't think. We'll see. We'll see. That's a good question. Yeah. Yeah. Okay, sure. So they have a background. Let's see how far their background goes. Ah, okay, okay. Maybe or I think would be plot the So do you so like it again, physics and calculus absolutely is needed to understand these things. Have you used and understand that we can have operators that affect wave functions, and depending how we change what those operators are to describe the state of it, the functional output would be changed or adjusted on it? Okay. 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 Yeah, great. And we might, like, what part, how does this relate to orbital shapes? Like, what part of this idea would give us shapes that are different? Let's see if I can find a better way. Okay. This is not helping. So before I start pasting like Wikipedia stuff, which may help or may not help. Like, if you're spinning something around and you don't move the center, what kind of plot would you say you're making? Because this might not help, but it is blah 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 blah. Like a ring, yeah, yes. What are shells versus subshells? Haha, let me just take this. What do they see in this picture? Okay. Or maybe that's not a question, that's more of a statement. So let's adjust a question. The orbitals, the pictures, are all stacked on top of one another. And the zero, or the origin, 0, 0, 0, is the protons. So each picture tells us where two electrons are, and we are stacking these pictures on each other to say here is the proton and here is the electrons in a probable area, not a definite area. Or we're just, I guess, kind of discussing the orbitals. The pictures are all stacked on top of one another, and the origin is the protons, which tells you there's two electrons. Let me be more clear. Let me answer that to start. And last of my life was my memory person. I don't think they're here. I don't see them. Dang. I guess with the Bohr model, I get how there is a nuclear with rings around it. We might need my iPad for this, so let's bring my iPad. I guess with the Bohr model, I get how there's a nucleus, which I've shown in black, with rings around it with electrons. In this model, Schrodinger, how are there layers, and how does the orbital terminology relate to that? So let's answer it in text, and then answer it in... down. So let's just take this same idea. So this up here is Bohr, written really badly. Let's do the same thing, but with quantum. We still have the protons at the center, but now instead of showing where the electrons are, I'm going to say they're in that space. That's the 2s node. And then last but not least, we're going to show 2p, which can be up here, down here, over there, back there, or back there. Let me see if I can find a better picture of this. Oh, great. Great! They found the image already. That's more statement. Can you be more clear about what's confusing you? Let's make sure we remind ourselves what the shapes are. And let's see if that at all, or at least my viewing of it. I don't love that the nodes aren't, I mean, I think the nodes are trying to be there, but they're not perfectly there. I'm going to be right back, check on my in-laws. Okay, so let me draw the nodes in on this picture a second. So first, there are only, so I'm going to do it in P. So these are for, what's an easy one? Let's do this one first. That's not an easy one. So first thing I'm doing, well, maybe I should just brush it. So I see this orbital in pink, this orbital in pink, and there is my node. My next one, oops. Now let's go back to my brush. Let's color in another p orbital. Let's go back to my brush. Let's do another p orbital, because there's 3 shapes. Each shape should have 1 node. This one is a little tricky to do, but it's approximately there for that one. Okay, now let's do the s orbital. So, oops, go back to green. Go back to my brush. The 1s does not have any nodes, and so it exists, technically it exists infinitely outward. There's the blue one, and its node is the crossing here, because there's also part of the 2s on that. So we'll get to that question in a second, because that one is based off of this one. We'll answer this one to start. And the last one, let's do purple. So, or I should be highlighting this. So this is the 1s orbital that I'm trying to describe. This is the 2s orbital I'm trying to, oops, the 2s orbital I'm trying to describe. And then in purple, I've cut it off a little bit, but the 3s orbital is like all of this space, with there being a node approximately right there is the first node for the 3s. And the next one in there, and we have a little bit of electron density that we can find in here, and here, and here, and here, and here, and here, and here. So it gets complicated. So it gets hard to draw on paper, but all the nodes from the math and individual pictures lets me see the nodes in a more complex picture, where I start to stack the individual pictures or shapes. The psi squared would be a line for 1s, a line for 2s, a line for 2, and then 3 lines, all the same, which I can approximate on my iPad and using the Orbitron, or maybe there's already a picture, so this is a version of it. This is kind of a version of it, which might help. I should say, And so let's draw an approximation, though, of some of the other ones, since I can't find a good picture of it. Oh, wait, was that no, it wasn't a picture. I don't want fonts. And so for 1S, let's look at it psi squared. So I'm going to walk away from this picture just for a second. And so we always have psi x. And so for 1S, it looks like this. And for 2S, and I did not draw this well, so let's be more careful with how we draw it, because I should not be crossing the X here. And so I'm stacking them. I'm stacking, or like, right, either we, in this picture that was kind of confusing to you, they're stacking all of the shapes. They're stacking the shapes into one picture. We can look at the shapes individually. This is looking at the shapes individually. Shapes, 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 shapes. But taking all these shapes together and more shapes and stacking them on top of each other, the artist would stack them like this. Whereas the mathematician could also say, well, I can represent these shapes as graphs, that I just stack these graphs on top of each other. And in this one, they're times them by the radial probability, the surface area of these things. And so what do I mean by conical nodes? How does that work? Also, why doesn't 1S have nodes? Because the standing wave that fits the answer to the Schrodinger equation is a wave that is not crossing the x-axis in two different ways. The wave is either up or, I shouldn't say it like that. Let's answer this one at a time. So first, let's separate these questions. Conical nodes are only used in the oddball DZ shape. It is not jelly beans, but has a, let's grab it, where was it? Here. But I want the one that shows the nodes. Did I already show one with nodes? Let's find one. Bring this into Paint. This, yes. And then why doesn't 1S have nodes? which are not present in a circular bound standing wave. I want to kind of make this a little bit smaller. So, because the simplest standing wave, the simplest psi solution, the simplest picture, the 1s orbital Great. Is this like the fact? Yes. it does fall apart eventually, but I can make a rough comparison to standing waves on a guitar versus standing waves around an electron. These pictures, which I can kind of grab these now together, go back to my paint. So it is that they're quantized, and I'm trying to fit these waves in, but to fit more of these waves in, I'm going to have more nodes as I have more and more solutions. The only way to allow for more solutions to the Schrodinger equation is to allow for more nodes to appear. And so the psi solutions, which the psi solutions are standing waves. Every psi solution is a standing wave. But there are many, many different psis we can come up with. We can come up with many standing waves, right? Every single one of these, right? Every time I look at the orbitron, every time I go to any of their wave functions, all of these are standing waves. All of these are solutions to Schrodinger's equation. All of these can fit the bounds that the calculus is setting, and the quantum numbers and the operators that we have to use to describe all of these things. All of these are standing waves. So let's see where this takes the students' thoughts now. And I love, love, love talking to this student about all this stuff. It brings me back to, I am sometimes too lost in my understanding of things. Or sorry, I'm too quote unquote, sometimes I'm too far gone. I need to get back to the student mindset where they are, in a lot of ways, a blank piece of paper. Chemistry is such a long way away for many of them, whereas I do it every day. Is the bigger orbital, 1s versus 2s versus 3s, the more chances for nodes, which allows for more wavelengths and energy. I don't like the word chances, but yeah, they are hitting on the right idea. What do I want to say? Yeah, I would say it's not a chance. The solutions of wave functions bound are becoming more complicated, and the nodes are the visual complication we see on psi, but they all fit the bound standing wave conditions needed around the protons. Instead of chance, say, I have to add more nodes to get another solution. For 1s, I needed no nodes. For 2s, I need one node. For 3s, I need two nodes. I need nodes to fit more solutions to the Schrodinger equation. Man, I would not. I'm not sure if I'm answering the question of the student very well. I'm just caught up on, this is the word I'm caught up on. I'm not sure what they mean by more chances. When you're doing the calculus, when you're solving Schrodinger's equation, and you're only allowed to use the angular momentum of S, so your angular momentum operator is set to 0, that limits some of your solutions to the Schrodinger equation. If you limit your answers to Schrodinger saying, I can only use angular momentum, that would result in p orbital shapes. I can add more jelly beans to it, and by adding more jelly beans, I'm adding more nodes to it, but I can never do the sphere answer. If the n quantum number is higher, 1s versus 2s versus 3, do we get more solutions to Schrodinger's equation? Each one is a solution. The 1s is one solution. The 2s is the second solution. The 2p gives 3 solutions. The 3s is helpful. Maybe. Okay, we're hopefully a little bit, we're probably a little bit further than we were before. And I don't, this isn't, maybe this helps, it's not technically accurate. The electron doesn't solve the Schrodinger equation. The electron just fills, or the electron adopts a solution to a wave function that is its lowest in energy. However, if electrons are already occupying a wave function that is a solution to the Schrodinger equation, if there's already electrons in the 1s solution, and I have to think of another solution, I'm going to look for the next lowest energy solution, and it's 2s. This is the electron. This is almost why you want to bring in electron configuration. Because what electron configuration is doing is it's saying, okay, when Schrodinger goes to solve his equation, the simplest way to solve his equation is to eliminate the angular momentum operator, setting L equal to 0, setting m sub L equal to 0, and saying n is equal to 1. Solve the Schrodinger equation with these simple solutions, and we get the most low energy Schrodinger solution, 1s. 2 electrons will always fill the lowest solution first. Then, if those 2 are full, the electron says, well, what's the other way the Schrodinger equation's been solved? The 2s electron then fits the next wave function. Still, we don't have the other 2 quantum numbers. They're set to 0, n is now set to 2. However, instead of solving 3s next, the next 2 electrons would say, when they're looking for a place to go, when we're looking for a wave function to describe the 5th electron, we don't solve the 3s wave function because it's too high in energy. We solve the 2p's 3 wave functions because we allow there to be angular momentum. We say now we have an L equal to 1, which has more solutions now for Schrodinger's equation, because now L equals 1 and m sub L is now 1, 0, and negative 1. So all of these operators, these Hamiltonians that change the wave function, because I've given them more variables to change, given them more variables to develop more solutions to Schrodinger's equation, the electron is always going to fill the solution that is the lowest in energy and that is available to it, that has not already been filled. So, a lot of weird stuff, but we're going to review on Monday. Yeah, and don't, and keep, please, come back if I stream on weekend. And Discord is awesome place to keep talking about this. And thank you so much for making me better-ish teacher and knowing the limits of my students. You are the real MVP. This is just my job. You're paying me for this, you know. Anyway, so wonderful. Let's even go back to the Discord and check to see what's going on there. So for now, we'll put that down, put that down, put that down, put that down, put that down. Okay, so we have a question on the quiz coming in. Let me check what I see on my end. Let's preview it. I don't think you use the carrots. Is maybe the answer. Oh, wait. Using the right. Just have to be a touch careful because we don't want to like do it. We don't want to commit any honor code violations. Okay, so they're looking at the question for argon in the tube. Anytime, anytime. Good luck. Okay, email's done, Canvas done. Pretty good work with some students, but we probably need to help them a little bit more with some other stuff. You know, I bet we could create an interesting resource while we have this last little bit of time. So, how do we want to do this? Do we make it as a website? No, we probably want to do just a Google Doc. All right, I'm going to call it for now. So hopefully we will have a stream over the weekend, as well as me kind of keeping in line with what's happening on Discord. And we will keep working together to try to get as high of a class average as possible.